Hello, everybody. So as our last topic for this particular sequence of videos, although there's going to be one more video after this, actually, it's a little just continuation of this idea. We're going to talk about change of basis. So then you have seen other examples, specifically the quadratic form example, that it's very useful to sometimes say that a certain vector can have different representations relative to different axis systems. So that means then that the actual point in that example of quadratic forms never moved. The graph didn't move, but the way we represented the points changed. But by looking at those collection of points in a certain axis system, it was easy for us to figure out what the graph has to look like. This is why changing a basis system is very convenient. So to do so, though, we need to have a fast way. We just need a fast way to go from one coordinate system to a new one. So let's say that we have a finite dimensional vector space V that will have two bases, B and C. The basis B will have U1 through UN, and the basis C will have V1 through Vn. Any matrix that sends the coordinates of a vector X in V relative to B to the coordinates of X relative to C is called a change of basis matrix. Now that's a lot of words. It's a lot of words. So I'm going to draw a picture to help you understand. So then you have this original vector space. What I want to do is I want to cut it out. I want to cut this out of the process. I want to look only at the coordinates, the way we represent vectors. So there's our vector space V with our two bases, B and C. The vector X is that point that I had before in the quadratic forms example. It doesn't move, it doesn't change. But X, though, if you look at it relative to the basis B, there are coordinates. Basis B just lays down its own axis system, its own graph paper on the vector space. So there are coordinates of X relative to B. You can then think of it as the coordinate as a way to map the vector X to its coordinates. So then we have some vector in Rn, which is the coordinates of X relative to B. But you could instead look at the vector space V in terms of the basis C. That would introduce a different set of graph paper, a different way to represent that particular vector space. So now X hasn't moved. It now has coordinates relative to C. So there is a way to take that vector X and map it to its coordinates. Now, when you're mapping via coordinates, you're going to the same space. You're going to Rn because the size of the vectors has to be the same, because the dimension is a fixed n. What I want to do is I want to cut V entirely out. I want to go and somehow figure out a way to map the coordinates vectors via basis B to the corresponding coordinate vector via the basis C. I want to send that vector to the vector. By doing so, we never have to look at the vector X at all. We never have to look at the vector space V at all. We're looking entirely in terms of Rn, which is convenient because we know a lot about that space. It's complicated enough, though, that you need to see a picture. You need to see like numbers, numerical examples first. You don't get lost with what I'm doing because it is very easy to do so. The actual computations at the end are easy, but understanding what's going on and why, that could be difficult to say. So let's say we have two particular vector spaces. Two particular bases, B and C. They're going to be a basis for R2. So every vector in R2 can be written uniquely in terms of the basis vectors in B and uniquely in terms of the basis vectors in C, but those coordinates need not be the same. So let's just take some vector in R2 and find its coordinates relative to basis C or basis B. I will choose, let's take the vector U1 because it's in R2. Let's take that vector U1 and notice it's a linear combination of the vectors in C. That linear combination uses the scalars 1 and 3. So the coordinates of U1 relative to C is the vector 1, 3. U2 is also in R2. So then I can find its coordinates relative to C if I wanted to. So U2, though, notice, is 2 times V1 plus V2. So the coordinates of u2 relative to c is the scalar vector 2, 1. So I now know u1 and u2 relative to c. Okay. Now, let's just take any old vector you like in R2. But I'm going to insist for our example that this vector that we have in our mind, whatever it is, this vector's coordinates relative to B is 2, 3. I want to know what are its coordinates relative to C, but I don't want to find out what X is. I don't want to actually add things up to find out what X is. I want to cut that out entirely. So to do so, it's not difficult. What we do is this. I know the coordinates of X relative to B. So I know how to form a linear combination of the basis vectors in B to get X. It's this guy right here. X has to be 2 times U1 plus 3 times U2. But then this is in R2. This is all that addition is in R2. It's in our vector space V. So I can find the coordinates of the left-hand side and the right-hand side relative to C. But when you do so, the coordinates of X relative to C would be the coordinates of that linear combination relative to C. And we remember, because the coordinates, the way the coordinates work, the coordinate operation distributes through sums and distributes through constant multiplication. So the coordinates of X relative to C has got to be 2 times the coordinates of U1 relative to C plus 3 times the coordinates of U2 relative to C. But I know those things. We just computed them. I know the coordinates of U1 relative to C. And I know the coordinates of U2 relative to C. So all I do is just replace. I literally replace this thing with what it equals to, and I replace this guy what it equals to, and I just add up what I have left over. That means I now know the coordinates of X relative to C, even though I never found what X was. Because remember, I'm trying to cut V and X out of the picture. I'm trying to go from coordinates to coordinates instead. But you might want to check your work. So let's see if we can see it's right. So then let's just check it. I told you the coordinates of this vector X relative to B, and we just found the coordinates of X relative to C. We have to be referring to the same vector X. Let's just find out what the vector X is now. So the coordinates of X relative to B was the vector 2, 3. So then I just form a linear combination of the basis vectors in B using those scalars, and I get the vet that X is 1, 8. Now I do it again. So I know the coordinates of X relative to C was 8, 9. So then I just form a linear combination of the basis vectors in C using the scalars 8, 9 in the order that we're in. And you get the vector 1, 8. Yeah, it's the same, right? Neat, right? That's because you have to get the same thing, because you're referring to the same vector. You're just using different coordinate systems to name that vector. Okay, cool. So you have that. What I'd like to do is do this faster. What I would like to do is I'd like to be able to invent a matrix that does this for us, that takes the coordinates of a vector X relative to B and just gives me the coordinates of vector X relative to C, so that I don't have to do what I just did every single time. And the answer is it's insanely easy to do. It's actually really easy to find this matrix, because just do what I just did, but without numbers. Let's suppose we have vector X, and let's suppose that we find out it as a linear combination of the vectors in base and relative to the basis B. So vector X is C1 times U1 plus C2 times U2. That's expanding X relative to the basis B. Just take on both sides, try to find out what the corresponding thing would be relative to the basis C. We know, though, that the coordinates of X relative to C has to be the coordinates of that linear combination relative to the basis C, but that coordinates distribute through constant multiplication and vector addition. So we get that statement. Thing is, though, I know U1 relative to C, and I know U2 relative to C. That's just this. Then I notice that I remember that linear combinations can be written as matrix multiplication. That's the reason we define matrix multiplication. What we did is to use that trick. So that's the same as this matrix multiplication. But the matrix 1, 2, 3, 1 times the vector C1, C2, The vector C1, C2, that's the coordinate vector of X relative to B. So the coordinate vector of X relative to C is the matrix 1, 2, 3, 1 times the coordinates of vector X relative to B. So now I can find the coordinates relative to C very quickly. Let's just see if what I did was right. Let's just convince you what I've done is right. So again, here we have a bunch of vectors. We have the two bases, same bases I've been using all this time. Basis B, basis C. We're talking about the vector space B. Let's just look at the vector X, but the vector X I'm not going to tell you. I'm going to tell you its coordinates relative to B. So its coordinates are going to be 1, 1. So then by what I just showed you, I can then find the coordinates of vector X relative to C by just multiplying the matrix 1, 2, 3, 1 on the left to the coordinates of X relative to B, and I get the vector 3, 4. So we're talking about the same vector X now. The vector V up here, that's the vector space V. X isn't moving. The coordinates can change, but the X doesn't change. Let's just check it. So if these are the correct coordinates, if I find out what X is then, by using these coordinates, I should then get the same answer. So the vector X, since X's coordinates relative to B are 1, 1, X would then have to be 1 times U1 plus 1 times U2. That's the vector 1, 3. But X's coordinates relative to C are 3, 4. So then X has to be 3 times V1 plus 4 times V2, and that's the vector 1, 3. And you have to get the same answer because you're referring to the same vector in the vector space. That vector's not moving. It's how you relate to it, how you represent it that's changing. And I think that's enough for that idea.